Okay. I feel like I should have been recording that talk also. Okay, I just started the video here. Well, are there any other questions from the homework? Yes?
How do you define a good confidence interval?
A good confidence interval?
Prediction interval.
A good?
So we have to compare two predictions.
Oh, what? Yeah. Yeah, that's, yeah, I guess it's a matter of interpretation and taste. So, are you talking about like the second problem? Or the second one, right? So one, the prediction intervals are kind of the same width throughout, and then the other one, the prediction interval gets wider as the x gets bigger, and you have to say, well, which one seems more appropriate for the model that we're talking about? And so you have to take into account what kind of data you're looking at. And so in this case, we're looking at subscription data and ad revenue. So I think in that case, it makes more sense that you're going to have a wider prediction interval when you have more subscribers than when you have fewer subscribers, because we're trying to figure out how much each page is worth in terms of advertisements. And I think it makes more sense that there's going to be more variation for the big ones. But you know, in another situation, it might make more sense to have even prediction intervals throughout. Okay, even amount of spread. So, you know, I think a key part of statistics is that looking at the data with no context is not going to be very useful. You always have to take into account where this data is coming from, the context of it, and what situations make sense. If without that, it's hard to say. It's hard to say anything is good or bad. So, okay, I don't know if that helps. All right, so today we're going to talk about weighted least squares regression. So when I was, you know, in undergrad and we learned regression and we learned weighted least squares regression, this was like, it felt very mysterious to me, but it's not that mysterious, okay? So first of all, let's talk about simple linear regression, okay? So in simple linear regression, how do we decide our coefficients, our slope and our intercept? It's written there, but yeah, we want to minimize this thing, right? Residual sum of squares. We want to minimize this quantity between the actual points y and our prediction line, okay? So whatever, so I think I drew this a long time ago in one of our earlier lectures. Maybe I can pull it up. We're trying to minimize, was it this one? Maybe not. Okay. Yeah, we're trying to minimize a regression residual sum of squares. Okay. With weighted least squares, okay, we're pretty much doing the exact same thing, okay, except we weight the squared residuals. Okay, so we apply weights to these residuals and we say this residual counts more towards this quantity. This other residual counts less towards the quantity. So, so we weight them. Okay, so with weighted least squares regression, we're trying to minimize the weighted residual sum of squares. Okay, so there is a weight w sub I given to every single point in our data. Okay, so if you have 50 data points, you get 50 weights. Every single data point has a weight. And so we can say this data point's important, this data point is less important, and the weights determine that. There's no there's no rule. You could use completely arbitrary weights. You could go through and say, I like this data point and I want the regression to accommodate it. So I'm going to give it a weight of 5,000. This data point's not very important. I'm going to give it a weight of 0.000001 or whatever. Even a weight of 0, which essentially is removing the data, that data point from the regression. There's no rules, but we have some strong guidelines. So you're not just making numbers up, right? You could totally just make up weights and make your own regression line that you want. I mean, it's still going to be a straight line, but we have that. Okay, so for simple linear regression, and this topic's going to be done really quickly. We estimate the slope this way, and we estimate the intercept this way. Okay, so I don't know if you remember this stuff. This is in one of the older lectures about estimating this. Sum of this xy and sum of squares x, and then once you get the slope, then you find the mean of y and the mean of x times that, and you get the intercept that way. Okay, weighted least squares, it's exactly the same. So in the textbook, there's this whole page of derivations, but it's like the exact same derivation. It's just now we throw w's everywhere. Okay, we just say this thing is weighted, and it's not just the x bar, it's the weighted x bar and the weighted y bar. So the weighted mean of x and the weighted mean of y. So we got weights for everything. Our intercept is weighted, all of this, okay? And the weighted means are, you add up the x times the weights and you divide by the sum of the weights. It's kind of customary to have the weights average out to 1, but there's no rule either, okay? And actually, they don't always. So anyway, you do this and you get this. Okay, so it's pretty much the same as simple linear regression, except we're just throwing weights everywhere. And all we're doing is we're just saying this data point is more important in determining our linear regression line than these data points, okay? But what this also does is if you have data where you have heteroscedasticity, okay, or you got that non-constant variance, when you weight the points with lots of variance to have less value, then their residuals also shrink, okay? Because the weighted residual, right? So the weighted residuals is the residual times, well, no, this is the weighted residual squares. So the weighted residual is the square root of this, okay? Which is going to be the residual times the square root of the weight. So when you have lots of spread in some areas and you reduce the weight, it makes your weighted residual sum of squares look more balanced. Okay, so the big question, the biggest challenge with weighted least squares regression is determining the appropriate weights to use. All right, and so there are some guidelines for how to determine the appropriate weights to use, and we also say if you can't use these guidelines, weighted least squares is probably not the best method to use. And so I encourage you to click this link and at least read through these responses. Both of these responses are pretty good in terms of how different ways to calculate the weights that you should use. Okay, so I'm just going to share maybe two important methods. Okay, so in some situations, the x that we have is measured at discrete points. So for example, in the cruise room and the number of crews we have and the rooms that we've cleaned, in that data set, X is recorded only for a certain number of crews. So let me see if I can pull up that graph. Where did it go? Ah. So let's do okay, so in this graph we see we have data only where X is 2, 4, 6, 8, 10, 12, and 16. Okay, so at each X, so it's not like X is continuous, X is very discrete. And so because of that, what we can do is we can estimate the variance of the Y at each X and use that as our weights. So we can say, okay, the variance here of these data points is this, and we're going to use that as a weight. Okay, so in this case, the weights that we would use would be the variance of our Y data. Okay, and so we're going to actually apply this to our cleaning data, and we'll see how that affects this as a way to control the variance, or control the non-constant variance. Okay, and so when, so what this says is when the variance is large, these points matter less in determining the regression. Okay. Here is one caution though, is that so here, at each data point or at each value of X, it seems like the Y values are fairly well behaved. But if you have some really high outliers or leverage points or something, estimating the variance directly, just saying, because what we're going to do is we're going to say, I've got these 1, 2, 3, 4, 5, 6 data points, and I'm going to take the variance of these 6 data points. But if you've got some outliers or something, maybe that's not the best idea. So in that case, they have a more robust method, and that is the square root of the deviations from the mean. Okay, so do you guys remember the scale location plot? Okay, so the scale location plot is this plotted against either your X or Y variable. Okay, the scale location plot, and we're just basically taking the inverse of that. We're taking the inverse of this term. So the question is, well, how do you figure out the Y hats, right? Because we haven't fit the weighted least squares line, so how do you figure out the Y hats that we're going to use? Okay, and believe it or not, you just fit the simple linear regression line, use that for your Y hats, and then you take the difference between each data point and your simple linear regression line, take the absolute value of that, and square root those. Okay, and that's totally fine. I know it's like, what, is that allowed? Well, simple linear regression in terms of the mean line itself is fairly robust. Okay, it's affected heavily by leverage points, but in terms of outliers within so if you had an outlier right here, the simple linear regression line doesn't really care. Okay, it cares if you've got a high leverage point, but if you got an outlier right here, it's not going to really affect it, whereas estimating the variance directly is going to be very heavily influenced if a point is up here. Okay, so you can just take the simple linear regression line and then do this, and this is it's pretty good. Okay, so and that makes sense because one of the key indicators of non-constant variance was the scale location plot, right? And so using this kind of thing from the scale location plot as a way to control our non-constant variance, saying that it increases or decreases, gives us is another way for determining weights. And then the last way for determining weights is using the number of observations. So, for example, your y sub I may not be individual points, but this itself might be like a summary. So it could be you took, this is like the mean of 10 people or something. So, so I think in chapter 4 in the exercises, one is you're trying to create a regression line between years of experience as a full professor, which is our x variable, and their income, which is the 75th percentile of their income. And so we see, people with lots of experience, they make lots of money type of thing. But, we have lots of people with, at certain areas where, we surveyed 30 professors with this many years of experience, and we surveyed only 17 professors with this many years of experience. And so in that case, we want to give more weight to the ones where we have more information, okay? And so we say the weight is the number of observations used to get that kind of summary statistic. Okay, so these are probably the three, safest ways to determine weights, okay? The word of caution is weighted least squares is not always the answer. This seems to be the caution for everything, that this thing may not solve all of your problems. So it's useful in situations where the variance in the model is not constant, but we have some way to estimate the variance, or some way to get an idea of the variance in the model, okay? And outside of these situations, probably weighted least squares is not the way to go. Yes?
In the previous slide, you said that the variance is inversely proportional to the number of observations. Does that just come from the formula of variance?
Let me think. The variance is inversely proportional to the number of observations. So we use this. Yeah. Oh, okay, so just think of like central limit there, right? Okay. So you've got the mean x, right? So what's the standard deviation of the sampling distribution? It's s over the square root of n, okay? Or if we were talking about the variance, it would be s over s squared over n. So as n increases, the variance is inversely proportional to the n, which is in the denominator there. Okay, so yeah. So as your mean increases, the variance of that mean term decreases with n. Not as the mean increases, as the sample size used to determine the mean increases. So yeah, this is just a consequence of how we determine variance for the mean or any kind of summary statistic. Well, I shouldn't say any kind of summary statistic, a lot of summary statistics. And, even the median, works that way. So, okay, so let's try this. We're going to load our data into R. And this is what the rooms and the cleaning crew's data looks like. Actually, this is probably a better plot right here. And so we can get, down here we have less variance. Over here we've got more variance, right? So how are we going to calculate this? Okay, so, well, let's So I'm going to use a dplyr here, and I'm going to take our cleaning data. So if we look, whoops, I should do so if we look at head of cleaning, this is what we have. We've got crews and we have rooms, right? So if you remember dplyr, what I can do is I can group by, I can take our cleaning data and I can group it by the number of crews, okay? So if I do that, the data is exactly the same, but now I've grouped it by crews and I see we have 7 groups, which matches what we have here. 1, 2, 3, 4, 5, 6, 7 groups here. And what I want to do is I want to summarize that. And what do I want to summarize?
The variance.
I want to summarize the variance, exactly. So I'm going to create a variable called var, and this is going to be, how do I calculate this? Which, well, I'm going to do variance of rooms. Oops. I don't need to capitalize that. Okay, and so it does it. That's like amazing, right? So, so dplyr is pretty awesome. If you couldn't tell, I'm a fan of this. And so I'm going to store this as a table called variances. So variances is a table that has summarized the variance based on the number of for each cleaning crew. Okay, and so what I want to do is I want to include this in my cleaning table, right? So if we look at cleaning, I have 53 data points, so I need to have a column with weights, right? So this is going to be, I need to have 53 weights here, okay? And so I can either attach variance or I can do 1 over variance, or it doesn't matter, okay? So basically what I want to do is, you know, when it sees the number 16 here, I want to attach 144 right here. And when it sees the 10 here, I want it to attach 62.83929. Okay, so how can I do this? So I'm going to create a lookup table, okay? So all I'm going to do is I'm going to take my variances table, which is this, and I'm going to take the second column, which are these values, and I'm going to call this lookup. So these are the lookup values that I want. Okay, so right now lookup is just these things, but I want to associate 9 with 2, and I want this associated with 4. And so what I'm going to do is I'm going to say the names of lookup. I'm going to give each of these, there's 7 numbers here, and I'm going to give each of these 7 numbers a name, okay? And the names that I'm using will be crews, okay? So I'm going to use the crews, the number of crews, as the names for these 7 numbers. Okay, so when I do this, I have associated these crews with these things. So the value is 9, and I can call up this value 9 by saying look up the name 2 in this thing lookup. All right, so I can say look up 4, look up 8, and it'll give me the associated number. Is that okay? Yes?
So you're trying to determine the weights by variance or by the number of observations?
So the way we're doing the variance, okay, is what we want to use the weight is for x equal to 16, I want to, you know, have an estimated variance. The variance is 144, and we're going to use that 1 over 144 as the weight of these things here, okay? And so I need a column here that says use 1 over 144, or, you know, 144, and then we can inverse it later. All right, So what I'm going to do now, so here, if I do lookup, if I do 16, it's going to say, you don't have 16 numbers in here. But if because these are names, I can do lookup quote 16, and it'll say, here's 144, or lookup 4, and it gives you that, okay? So this is what we're going to do. We're going to take our cleaning table, okay, and I'm going to do cleaning crews, and I'm going to do as.character. All right, so as.character of cleaning crews is going to say, take this column here and just say 16, 10, 12, 16. Okay, 16, 10, 12, 16, stuff like that. Okay, and we're going to put that inside lookup. So I'm going to take all of these numbers and put it inside lookup, and it will return the number that I'm looking up, right? So I take this and I do lookup bracket bracket. So this is known as this is one of the magic of subsetting in R, okay? Because we're using our brackets, and it gives me back all of these numbers that I need, right? And so now I just have to take this and bind it, column bind it to our table. What am I saying? Cleaning table, okay? So I'm gonna do data.frame, and we're going to take cleaning, and we're going to do lookup cleaning, okay? And so when you're doing a data frame, don't do cbind, because cbind is for matrices, so it's going to try to coerce everything, okay? So we do this, and look at that, it works, okay? But this is a terrible, terrible thing, so actually what I should probably do is I'm going to call this vars or whatever. Okay, and then I'm going to do it again. Data frame, cleanup, and just attach vars. Okay, and that looks much better. So we've got it. So we've got all 53 weights that we want, or actually this is the inverse of the weights, so the weights will be 1 over vars. Okay, so I'm going to call this, actually I should call this our new cleaning table. Excuse me. And so now we can do our cleaning model, okay? So I'm going to create weighted cleaning model, which is going to be a linear model explaining rooms as a function of crews, okay? Except all we have to do weighted least squares, we just give it weights. Okay, weights is going to be 1 over vars, okay? That's our column here, right? And we say this comes from our data table, cleaning. And it says, okay, I did it. So we do a summary of our weighted cleaning model. And this is it. Let's compare our summary of just the regular old cleaning model. Okay, so if you look at the regular old cleaning model and the weighted cleaning model, in terms of the slope, it's only a little bit different. Okay, the intercept changes. Okay, but let's see. So our R squared for the regular cleaning is just a tiny bit lower, and so here, let me actually I don't know how to plot the yeah. So let me just do plot cleaning $, crews, and cleaning $, rooms, okay? And so I'm going to do AB line cleaning model. Okay, right? So this is the best fit line from the regular, okay? And now I'm going to do this, and we're going to do weighted cleaning model. Okay, so I don't know if you can tell, but it's just the weighted cleaning model. Just that's all it does. Okay, so it doesn't seem like it makes a huge difference here. Okay, but when we look at the residual plot, then you will see the difference here. Okay, so we can look at cleaning model $ residuals. Okay, and then when we plot this, if we plot cleaning $crews against cleaning $residuals, cleaning model residuals, we see this this bad pattern, right? Okay, so the regular old linear model doesn't have the weighted residuals, so we have to call a function called weighted residuals, okay? And all we do is we just say, okay, give me the weighted residuals of the weighted cleaning model, okay? This is not going to work if you, I think, well, actually, I've never tried it. Let me see if, so you do weighted.residuals of, your weighted cleaning model. Let me see what will happen if I ask for weighted residuals of a regular old model. I think this is just the same as the regular old residuals. Let me see. Yeah, so these are, so if you ask for weighted residuals and there's no weights, it just gives you back the residuals. But with the weighted residuals of the weighted cleaning model, I'm gonna sneeze here. Maybe not. Okay, I'm gonna plot these, okay? So I'm gonna call these weighted residuals. And I can plot crews against weighted residuals, and I think you'll see the problems of heteroscedasticity have been taken care of, or at least addressed. Okay, so with weighted residuals and a weighted model, we see, so here we've got that funnel pattern, which we know is bad, and over here it looks better. Okay, even though in terms of the linear regression line, it's like it doesn't seem like it has made much of a difference, which it, for all intents and purposes, it really hasn't. Okay, but with the weighted residual model or whatever, it takes into account and it shrinks those residuals, and so now we can talk about constant variance in a weighted model. I guess that's all I have. Yeah, questions?
So this is, in a way, you're trying to make the data set look better, and so that you're able to do analysis, right? And how do we transform this back when we're trying to interpret it?
Yeah. Okay. So, yeah, I didn't write the code here. So, basically, when you create a prediction interval now, okay. So under the regular, so you can't do predict. So prediction, so if you use the R command predict, it creates, it assumes constant variance. And so to make a prediction interval, it gets more complicated. You've got to transform your prediction interval back into taking into account the spread. I want to say the shortcut is you just multiply the plus or minus part by square root of w. But I better double check before I say that. So I have to append my code here with how to do a proper prediction. So. But yeah, we do weighted least squares to address the fact of non-constant variance, and then when we're going to use it for predictions, we have to take that into account. And basically, in places where you've applied low weights, the interval for your prediction will be super wide because you gave less importance to those values. And the places where you've given high weight to the values, you can have a smaller prediction interval. Okay, so so that's kind of how it works. And I didn't. I was up late and I was like, this is all I'm gonna write for now. So okay, so that's that. So we'll end there. A couple of minutes early. Wait, more questions? Yes.
Yeah. So, there's like weird variances between the points, right?
Okay.
What if the variances mean something, and what we're doing is to just, kind of discount the variances?
Yeah, that's a good point. And so, yeah, if you see lots of variance in certain area, it is a good question to say, why do I see lots of variance here? But I wouldn't say we're discounting it. We're trying to accommodate it in our model. In that, remember, when we're creating a regression line, we're creating a regression line for the mean of the relationship between x and y, or whatever it is that we're looking at. So it might be that for these values, there's lots of variance, meaning the true mean is right here, but the values are all over the place. And I think if you want to use weighted least squares to address that, that's okay. But yeah, always in the context ask, why am I getting huge variance for these things? So, maybe if we looked at miles per gallon and, I don't know, cost of a car, we might see lots of variance for cars in the 20 to 30 grand range, just because almost all the cars people drive are in this range or something, okay? Whereas, I don't know, other things, it's different. So, so something like that. I don't know. Yeah. Okay. Well, have a great weekend. We'll see you guys on Monday.